Hello and welcome everyone to this lively exploration of cloud data warehousing and its remarkable influence on modern analytics. Today we are delving into the intricacies of Snowflake, Amazon Redshift, and Google BigQuery, three powerhouse platforms that have drastically transformed how organizations store, manage, and analyze data. Our journey will combine both theory and practice, shedding light on architectural fundamentals, integration strategies, security best practices, and performance tuning. Along the way, we'll also discuss the growing interest in data mesh and data federation, ensuring we leave no stone unturned in this grand tour of cloud data warehousing. So sit back, relax, and let's embark on an engaging ride through the evolving world of data. To begin, I want to ground us in the basic concept of a data warehouse. A data warehouse is a specialized system that aggregates and stores data from various sources, such as transactional databases, application logs, and third-party streams, for the sole purpose of advanced analytics. Unlike your everyday transactional database, which is optimized for speedy insertion and updating of records, what we call online transaction processing, or OLTP, a data warehouse is tuned for online analytical processing, or OLAP. OLAP focuses on complex queries that help you identify trends, spot anomalies, and generate insightful reports. If the term OLTP feels unfamiliar, think of it as the sort of database where your shopping cart transactions and banking records are stored, frequent updates, single record lookups, and minimal summarization. OLAP, by contrast, is the slow and steady aggregator, combining millions or even billions of records to produce meaningful insights for long-term strategy and decision-making. Organizations typically realize they need a data warehouse where they find themselves buried under a mountain of data, with the needs to deliver analytical queries faster and at a scale that traditional databases simply can't support. If you're noticing that your transactional database is groaning under the weight of endless complex queries and your business intelligence reports take ages to run, it's a sign that a proper warehousing strategy might be in order. This point often arrives when data grows in volume, velocities pick up, and the diversity of data sources increases. In other words, if you've got data streaming in from Internet of Things devices, logs from distributed applications, and batch uploads from ancient on-premises systems, you've likely crossed the threshold where a data warehouse becomes essential. Early data warehouses were not exactly the pinnacle of convenience. They demanded huge upfront costs for hardware, required teams of IT experts to maintain, and often lacked the elasticity to handle surges in analytical workloads. Upgrades typically meant shutting down systems, installing new hardware, and hoping that your estimates matched future demand. Such capacity planning often felt like guesswork, and if you guessed wrong, it either meant wasted resources or performance bottlenecks. The shift to cloud-based data warehousing revolutionized this model by introducing the ability to provision resources on demand, pay only for what you use, and scale up or scale down almost seamlessly. This transition fundamentally changed how organizations budgeted for and operationalized their analytics workloads, drastically reducing the time and money spent on routine maintenance. Before we examine Snowflake, Amazon Redshift, and Google BigQuery in detail, let's briefly touch on some key terminology that might pop up throughout our session. When we say schema evolution, we're talking about the processes and strategies used to adapt the structure of your data warehouse as the data itself changes over time. This often involves adding new columns, modifying data types, or rearranging tables so that your queries remain accurate and efficient. Data quality, on the other hand, deals with ensuring that data remains consistent, accurate, and reliable, which often involves employing governance policies and automated validation checks. If you hear the phrase real-time data streaming, it generally refers to pulling in data as it's generated, often through systems like Kafka or Kinesis, rather than ingesting everything in huge hourly or daily batches. Each of these concepts might seem like a small piece of the puzzle, but collectively, they form the bedrock of a successful data operation. Let's begin our deeper dive with Amazon Redshift. Redshift was one of the first widely adopted cloud data warehousing services when it emerged in 2013. It operates on a principle known as massively parallel processing, often shortened to MPP. MPP describes a setup where a query is split into smaller subtasks that run simultaneously across multiple compute nodes, thereby speeding up analytics that might take far longer on a single machine. Redshift also integrates tightly with the broader AWS ecosystem, making it especially attractive to organizations already using tools like Amazon S3 for data storage or Amazon Kinesis for real-time streaming. If you're unfamiliar with Kinesis, it's an AWS service for ingesting real-time data streams such as those from application logs or Internet of Things devices, which can then be funneled directly into your data warehouse. Redshift offers options for encryption using AWS Key Management Service and allows you to implement fine-grained access controls via AWS Identity and Access Management, which helps keep data safe and ensures that only authorized users have access. Some might argue that Redshift's query optimization strategies can require manual tuning, such as choosing the right distribution styles for your tables or deciding on the correct sort key. But this can also be a boon if you relish hands-on control. Performance can be impressive if these optimizations are done correctly, and you can manage costs by picking the right cluster size or even leveraging Redshift serverless, which introduces a pay-per-query model. A quick note, Redshift's approach to scaling might involve some downtime or performance hits if you're resizing nodes, so it's not entirely seamless. However, it remains a stalwart solution for organizations that value tight AWS integration, especially if their data workflows are deeply ingrained in the Amazon ecosystem. Snowflake, by contrast, is a cloud-native data platform that famously decouples storage from compute. Decoupling is a design pattern that separates your data storage from the computational resources needed to query that data. In essence, you pay for storage costs on one side and compute usage on the other, allowing you to fine-tune each dimension independently. If you want to run a massive series of queries, you can scale up compute temporarily without incurring huge storage fees. And if you need to store petabytes of data but only run small queries intermittently, you won't be charged for idle compute resources. Snowflake also introduces concepts like micro-partitioning, which automatically organizes data into small chunks to optimize query performance, and automatic result caching, which can dramatically speed up repeated queries. One of the strong suits of Snowflake is its multi-cloud operability, meaning you can run it on AWS, Azure, or Google Cloud, and therefore avoiding lock-in if you prefer to keep your options open. Snowflake also offers advanced governance features, including role-based access control and data masking, which simplifies compliance with regulations like GDPR, the European Union's General Data Protection Regulation, and CCPA, the California Consumer Privacy Act. Under GDPR, for instance, personal data is subject to strict rules about how it's processed and stored. So having the ability to mask or restrict certain columns is invaluable. Though Snowflake is often praised for its user-friendly interface and innovative architecture, it shares similarities with its competitors in terms of elasticity and security. So while these features are indeed differentiators, they're not entirely unique in the wider cloud data warehousing landscape. That said, the platform's simplicity in scaling and consistently strong performance across different clouds do set it apart for many use cases. Now let's talk about Google BigQuery. BigQuery is known for its serverless architecture, which means you don't have to manage any underlying infrastructure. This allows you to focus purely on writing queries and extracting value from your data rather than worrying about spinning up or maintaining clusters. If you're curious about what serverless entails, it's essentially a model in which the cloud provider, Google Cloud in this instance, automatically allocates and deallocates compute resources as needed. So you only pay for the queries you run and the data you store. BigQuery is deeply integrated with other Google Cloud services like Cloud Pub Sub, a messaging service for streaming analytics, and Cloud Dataflow, which supports advanced data processing pipelines. This makes building real-time data streaming architectures simpler if you're already invested in the Google ecosystem. BigQuery employs a columnar storage format and a distributed query engine known as Dremel to process large data sets at speed. It also has features for real-time data ingestion, so you can push streaming data directly into BigQuery, a vital capability if your organization needs insights almost immediately after data arrives. BigQuery's security model relies on Google Cloud's identity and access management, letting you manage permissions with a high degree of granularity. It also supports encryption at rest and in transit by default, aligning with compliance requirements in many industries. In terms of cost, BigQuery's pay-per-query model can be a double-edged sword. It's economical if you run queries intermittently, but costs may ramp up if you're scanning large data sets too frequently. There is a flat rate pricing option for enterprises needing predictable costs, so you can mitigate any surprises. While Google BigQuery originally gained a reputation for being especially powerful at large-scale analytics, it's worth noting that both Snowflake and Redshift have narrowed the gap on many performance metrics, so these differences can be situational rather than absolute. All three platforms, Redshift, Snowflake, and BigQuery, offer various advanced integration patterns for modern data ingestion. This might include real-time data streaming architectures using Kafka or Kinesis, which allows messages or small batches of data to flow continuously into your warehouse for near-instant insights. Regardless of which streaming tool you choose, each data warehouse has a connector or interface to ingest these streams efficiently. Managing schema evolutions, such as adding new fields or changing data types, can be handled through automated pipelines that detect new structures on the fly, although the ease of this process differs across each platform. Data quality at scale can involve a combination of designating landing zones for raw data, transformations to clean and validate records, and finally, curated zones that analysts and data scientists can trust. While the details may differ slightly, the broad patterns remain the same across most modern warehousing solutions. Security and governance are increasingly critical topics. As organizations grapple with stringent regulations and heightened customer expectations around data privacy, fine-grained access control means the ability to specify exactly which users or groups can see or modify particular data. In practice, this might entail allowing only the finance department to view certain salary columns or restricting personally identifiable information such as names and addresses from the marketing team. Governance also extends to data lineage, which is a method of tracking the origin, transformations, and usage of data over time. You could visualize data lineage as a map of your data's entire life cycle, where it came from, what changes were applied, and who accessed it. This map is important when you're doing audits or trying to comply with regulations like GDPR, which gives citizens in the EU certain rights over their personal data. All three platforms support different degrees of lineage tracking, though many organizations augment built-in features with third-party solutions for more robust metadata management. In a nutshell, securing data while maintaining compliance is no small task, but each of these cloud data platforms has put considerable effort into offering tools and integrations that help streamline the process. Performance optimization is a topic close to the hearts of data engineers and analysts everywhere. Each platform has its own strategies for query optimization. Redshift, for instance, benefits greatly from choosing the right distribution keys and sort keys, which define how data is physically laid out across nodes. Snowflake automatically manages clustering via its micro-partitions, but you can fine-tune how it caches certain results or scale up your virtual warehouses for especially large workloads. BigQuery, in turn, doesn't require the management of indexes or distribution keys, but you do need to be mindful of how much data each query is scanning because that directly affects costs. A common approach to controlling these expenses is to employ partition tables or table sharding so that you only query subsets of your data. Caching and materialization strategies can also drastically reduce query times and control costs across all platforms. Materialized views, for instance, pre-compute the results of a query and store them for rapid retrieval, sparing the data warehouse from having to rerun complex joins or aggregations each time. While these differences are real, they sometimes overlap in ways that can make them feel less like absolute differentiators and more like alternative paths to a similar goal. Most modern cloud data platforms support caching and auto-scaling in one form or another, but each implements it slightly differently, resulting in diverse performance profiles depending on workload patterns. Turning our attention to data mesh and data federation, we step into more conceptual territory that addresses the question of how to manage and share data across large, possibly decentralized organizations. A data mesh is a strategy that treats data as a product and distributes ownership to domain teams, each responsible for their own data pipelines and quality controls. This approach is meant to reduce bottlenecks by empowering the teams who actually understand the data the best. However, implementing a data mesh is easier said than done. It requires not just technology shifts, but also organizational and cultural changes. Data federation, on the other hand, is the ability to query and combine data residing in multiple systems, potentially across different clouds, without necessarily copying everything into a single warehouse. For instance, you might have customer data in Redshift, inventory data in Snowflake, and marketing analytics in BigQuery, but you want to run one query that seamlessly integrates all three. While each platform offers its own connectivity features or external table concepts, achieving full federation can get tricky when dealing with diverse data formats and security policies. It's more than just linking a few systems. It's about creating an architecture that allows queries to be executed optimally while respecting each domain's ownership rules. This is a hot topic, and many solutions are emerging to handle cross-platform data queries, though it's still an area where the industry is rapidly evolving. Now, the question often arises, how do you choose one platform over another? And are the differences truly game-changing? The reality is that some of these distinctions can be subtle. Snowflake's multi-cloud approach might be absolutely crucial if you have strategic requirements for running workloads on multiple clouds. But if you're an AWS first shop, maybe that isn't your highest priority. BigQuery's serverless model can be superb if you want minimal overhead and enjoy Google's ecosystem, but it can become more expensive for extremely active query workloads if you're not using flat rate pricing. Redshift might integrate flawlessly with your existing AWS services and give you manual control over distribution keys and node types, but you might prefer a platform that requires less hands-on tweaking. There's no single winner across all dimensions. Each has strengths that might matter more or less depending on your unique constraints, objectives, and existing technology stack. It's also worth noting that all three platforms are continuously adding new features. So even if you find a slight performance gap or cost difference today, it could change in the near future. One of the most interesting developments in modern data warehousing is how quickly new data integration patterns are emerging. Real-time data streaming using Kafka or Kinesis is becoming mainstream as companies want insights the moment data is generated rather than hours or days later. This real-time capability is invaluable for use cases like fraud detection, where you need to act on suspicious activity right away, or live user analytics for an app with millions of global users. Modern data ingestion now includes semi-structured or unstructured data from sources like JSON logs, social media feeds, or IoT sensors, which require flexible schemas and robust ingestion pipelines. Platforms are stepping up their game by offering native support for these data types, or by providing easy integration with tools that can transform and load the data. Schema evolution strategies ensure that this dynamic data can be integrated smoothly without causing errors or forcing you to rebuild your pipelines from scratch. From a security perspective, fine-grained access controls are becoming ever more sophisticated, letting you specify who can do what down to a row or column level. This can be vital when you have to comply with data privacy regulations like GDPR or CCPA, which might require you to protect personal data or allow users to request their data be deleted. Data lineage is also critical in these compliance scenarios because regulators may ask you to demonstrate exactly where users' data has traveled. This lineage data ensures you have a traceable record from the moment the data entered your system all the way through to the final report that used it. Implementing lineage and governance at scale can be complex, but each one of our three platforms offers at least some degree of built-in tooling or partnerships with third-party vendors to facilitate that process. Performance tuning often feels like an art form as much as a science. You can get huge speed gains by selecting the right distribution key in Redshift, carefully designing your micro-partitions in Snowflake, or cleverly partitioning your BigQuery tables. Another important aspect is cost management, as the pay-as-you-go model can either be a blessing or a curse. Scheduling queries, caching frequently used results, and implementing materialized views can all reduce the amount of data scanned or the number of computations performed. This becomes particularly important in large-scale operations where a single query can scan terabytes of data and add significantly to your monthly bill. All of these platforms provide dashboards and tools for monitoring and controlling spend, and third-party tools can further enhance cost visibility. Finally, data mesh and federation remain some of the more advanced frontiers in data architecture. Implementing a data mesh requires a shift in how you think about accountability and ownership, placing it squarely in the hands of the teams that produce or heavily rely on particular data domains. Federation lets you unify your analytics without duplicating massive data sets, but can introduce complexity around performance and security if you're not carefully managed. If you're moving in this direction, be prepared to invest in robust metadata management, a well-defined governance framework, and possibly new roles or responsibilities within your organization. All in all, cloud data warehousing has become a keystone for modern enterprises that want agility, scalability, and the ability to glean real-time insights from enormous volumes of data. Snowflake, Amazon Redshift, and Google BigQuery each represent strong, mature offerings in this space. They share many similarities such as MPP underpinnings, scaling capabilities, and robust security controls, yet maintain certain unique traits that can become true differentiators depending on your situation. In some instances, these differences overlap to the point where they aren't as pronounced as marketing materials might suggest. However, in other scenarios, those same seemingly small variations can be pivotal. The key is to align the platform with your organization's priorities, whether they revolve around cost control, multi-cloud deployment, tight ecosystem integration, or effortless serverless operation. As data volumes and complexities continue to surge, the next wave of innovation is likely to center around even tighter integration with AI and machine learning, more automated governance and lineage tracking, and a continued push towards real-time data processing as the default rather than the exception. Data warehousing will remain a cornerstone of enterprise intelligence, forming the bedrock upon which advanced analytics and data science are built. By mastering the tools and techniques we've explored today, ranging from Kafka-based streaming pipelines to fine-grained access controls, and from caching strategies to data mesh implementations, you'll be well positioned to harness the full potential of your data. And that, after all, is what this adventure is really about: transforming raw data into insights and insights into smarter decisions that propel your organization forward. Thank you for joining me on this journey into the world of Snowflake, Amazon Redshift, and Google BigQuery, and I hope it leaves you energized to tackle your own data challenges with renewed creativity and confidence.